In this example, we're looking at particles A and B, which are connected by a cable pulley system that's shown. A is able to move along a smooth rod, which is attached to a shaft. The shaft is initially turning with a rotation rate of omega. B is allowed to move along a smooth vertical guide, which happens to be the shaft. We know where A starts out, 0.8. We know omega at that position, 6 radians per second. And A, once we let it go, A is going to move outward. Of course, if A moves outward, then B moves up. And what we want to find is the angular speed of the arm OC at that position, and we want to know the speed of particle B. Okay, so let's look at an F.B.D. of A and this arm. Well, the forces that are acting on this, we've got this tension force, which I'll call FAB. Then there's some reaction forces back here at O, acting on this arm. And the view that I'm looking at here is the top view. And the thing about this is that from this FBD, we make the conclusion that although the tension force is there and the reaction forces at O are there, all three of those forces act through O. So in using the angular impulse momentum equation, we can conclude that the summation of moments about O is a zero. What does this say? Well, it says for A that the angular momentum about O is a constant. Whatever it had before, it has at position 2. Well, HO1. We know by definition it's the mass position of A with respect to O crossed with the initial velocity for A1. So O to A, that's the radial distance R1 in ER. I'm going to use a radial unit vector ER in E theta like this. And the initial velocity for A, it's going to be, in general, there's an R dot ER and R omega 1 E theta. Well, it says that initially A is stationary relative to that arm. So R dot initially is a 0. So all that we have left here is an M R1 squared omega 1 ER crossed E theta is a K. Angular momentum about O for time 2. Well, the R vector is going to be the new distance R2, ER, cross with the velocity. We don't know what it is, but we'll write it in terms of a polar description and see what we can get from this. Like this. ER cross with ER, that's always a 0, any vector cross with itself. So what's left here is M R2 squared omega 2 ER crossed E theta is a K. So since angular momentum is conserved, set those expressions equal to each other. M R1 squared omega 1 is equal to M R2 squared omega 2. So we see that once A has moved out to its new, once A has moved out to its new position, the rotation rate of that arm, omega 2, is just the ratio of R1 to R2 squared omega 1, so we know all that information. So that tells us what the arm is doing. Now we want to find out something about the speed of A. Of B. How do we get that? Well, what we know is that the velocity, the speed of B, I'll say, is equal to r dot. The reason for this is that as A moves out, its radial component of velocity has to be the same as the speed of B because of that chord. But we don't know that. Right up here, where that appeared, we didn't get anything because ER cross with itself is 0, so it just disappeared. So we have to come up with some other way to get that. Well, one thing we can observe is that energy is conserved. And if we look at A and B together, we can say that energy is conserved. So write down T1. T1 is 1/2 m v A1 squared plus 1/2 m v B1 squared. Well, it's said that A is initially at rest relative to the arm. So r dot is a 0. So since r dot initially is a 0, so is VB1. Then the only thing that's left here for VA1 is R1 omega 1 squared. T2. For position 2, we have the 1/2 mv squared for each one added together. And so for VA2, we have both radial and transverse components. So this is R2 dot squared plus R2 omega 2 squared. That's for A. For B, 1/2 mv squared, we said above that the speed of B is one in the same as the radial component of velocity for A. So we have that. In terms of V1 and V2, I need to define my datum. And what I'm going to say here is that my datum position is going to be where B is at the start. So by that definition, the initial potential for the system is a 0. V2. Since B moves up, it's going to be a plus sign. mg, and the height change for B, well, the height change for B is equal to the distance that A has moved out on that arm. So it's R2 minus R1. We have that information. So since energy is conserved, T1 plus V1 is equal to T2 plus V2. So that's T1. We said that V1 was a 0 because B starts out at the line that I could choose for my datum position. For A, T2 is 1/2 m R2 dot squared plus R2 omega 2 squared. And for B, it was 1/2 mv squared, and V was equal to just R2 dot squared. Potential is mg R2 minus R1. So from this, we have one equation and one unknown. That's R2 dot. So I'm going to say then that R2 dot squared, that's going to be equal to, let me see if I can do this in my head, it's going to be 1/2 m R1 omega 1 squared. I'm bring over my potential term, which is mg R2 minus R1. And then I will have a subtraction here of minus 1/2 m r2 omega 2 squared, like this. And I need to multiply this by, I guess I have two terms. I should make that clear. I have an r2 dot squared here and r2 dot squared. They both have an 1/2 m in front. So that's going to be just, in the end, that's going to be a 1 over m with a square root in front. This is equal to VB2. Again, the reason for that is that for every distance that A moves out, B moves up the same amount. So the radial component of velocity for A at time 2 is the same as the speed for B. We did quite a bit of work here. Let's go back to see what we did. Well, the first thing we did was look at a free body diagram of A, and the only forces acting on A pass through point O. No moments about O, therefore angular momentum about O for A is a constant. Write HO initially. 1/2, is equal to m r1 squared omega 1k. Do the same thing in position 2. We get m r2 squared omega 2. Set those equal and we get omega 2. Now, in order to find what's happening with B, we use conservation of energy for A plus B together. So initially we had 1/2 mv squared for A. That's given information. For T2, 1/2 mv squared for A plus 1/2 mv squared for B, and simply recognizing two things. A has two components of velocity, so we have both of those there. And the other thing is that the speed of B is the same as the radial component of velocity for A. Potential, we write that down, we put all our things together, and we solve for R2 dot, and that's equal to VB.